Welcome to the next video lecture of control system. So in this lecture, we are going to discuss about the how a DC servo motor will be converting into mathematical modeling in terms of the transfer function. Okay, so transfer function of a DC servo motor. So the topics to be covered is the what exactly is a DC servo motor and how it will be converted into DC transfer function, DC servo motor into mathematical modeling as a transfer function. So first, what is DC servo motor means? So DC servo motor basically many people don't know, but it will be mostly will be in this type of structures which will be using in the academic section, but it will be mostly in advanced place also. It is using like in a robotic arm. If you are seeing like it as a robotic arm, so like its fingers are moving or its arm is moving, robotic arm. If it is moving and taking from one place to one place, so this is the thing which is using in a inside the motor operation will be there. So what exactly the DC servo motor means? DC servo motor mostly used in electrical and any many places like it as in robotic field and also aerospace also. In aerospace, whatever that controlling of the drones and drone capturing and the drone movement and whatever the drone whatever things will be there, like it will be moving in the direction and the speed of the rotation each and everything. So that will be always using in the servo motor because it is very less space and also very less size and very low cost also. Okay, and when it comes to the basic thing, so this is how it will be there. Okay, so the basic structure of the DC servo motor, it will be explained in the machine video lectures, but it is basically it will be look like this. Inside is DC servo motor. So what exactly a DC servo motor means? The DC servo motor is a motor which can able to control and also it will give a very high precision and high accurate and position also. If you want to rotate like it as a only 10 degrees of the rotation also it can able to do. If you want to rotate only 90 degrees means it will move also only 90 degrees. If you want to do a 360 degrees operation and also it need to get anti-clockwise and clockwise, both need to be done after some time to some time means it can able to done. That is a speciality of the DC servo motor. So DC servo motor will be there. So this is the basic DC servo motor basic block diagram, which is using with respect to the Arduino platform. Arduino is one of the controller which is controlling the servo motor position. That means the position means it is rotating, either it will be in the clockwise or it will be in the anti-clockwise, or it need to be rotating in the 90 degrees or it need to be rotating in the 10 degrees, however it need to be. So that need to be controlled by with respect to this one. This is the basic block diagram of a DC servo motor. So this potentiometer means it is like it as a wherever we can able to easily control. If you want to increase the speed, we can able to increase the speed. If you want to decrease the speed, we can able to decrease the speed. Like that it can able to done. This is how it will operate. This is the servo motor arm. That means that is whatever that structure of wheeling will be there. That is that one. And the next one is the transfer function. So this video will be a little bit lengthy, so be careful, and also it will be included with many equations, and also be careful because in each equation itself it is considers when I'm giving one equation means it is a consist of a back steps of at least nearly 3 to 4 steps will be there. So I'm giving a final steps of that every equation. So because to make the video to be crisp and also to understand very finely. Okay, transfer function. So the relation between what are all the things we are considering is the relation between the input voltage and motor angular position. So because we need to control the position of the motor means then we need to understand how exactly the motor is in which position. That means either it need to be in a clockwise or anti-clockwise or which degrees of it is there. So it need to be done. How it need to be controlled, how it need to be take the transfer function is with respect to the Laplace transform and also motor dynamics. Motor dynamics means we need to take the position, we need to take the angle, we need to take the torque, we need to take the velocity, we need to take the voltage, what is feeding to the system on motor also. So these are all the things will be there. So this is how exactly it will be operated. This is the basic block diagram controlled in the transfer function. It will be comes in whenever you are going into very control place controlling thing. But right now we are discussing about only the transfer function. That means mathematical modeling. So we are not discussing in depth of this diagram itself. Okay. And the next one is about what are all the components and what are the assumptions, because assumptions and components are very much important whenever we are drawing a mathematical equipment or mathematical modeling, because each and every parameter we can't able to consider, each and every parameters we can't able to include in a mathematical statement. So that's why we need to take some assumptions. What are the assumptions we are taking is we are considering is the armature control only, because the motor can be controlled with respect to the armature. We can able to control with respect to the voltage. We can be able to control with respect to the frequency. We can able to control with respect to the resistance. Many ways the motor can be controlled. But here we are taking considerations of the armature control only, and also constant field flux. We are taking consideration the field flux is always a constant, and also linearly time invariant means it is not varies with respect to the time. It is varies, it is not depend upon the time. And also ideal condition, that means initial conditions will be zero in that conditions. And also what are the main components means, that is resistance, inductance, force, and also magnetic flux, and also the whatever the torques and each and everything for flowing on the motor. Okay. And from the Kirchhoff law, what we are going to derive is this is the final equation. That means VA, that is input voltage, RA, that means what are the resistance of the motor, and the inductance of the motor, whatever it will be there, and EB means the back EMF. Every motor will have a back EMF will be present on that one. So that why we need to consider the back EMF also, that EB is the back EMF. So that back EMF of the motor. So back EMF generated by the motor. So next one is what exactly the mechanical equation, because we are seeing in the electrical equation with respect to the Kirchhoff laws, but we need to say the mechanical equation also, because we need to get the considerations of that one. So then Newton, from the Newton's law of rotation, because as it is a rotational mechanical body, so we need to see the Newton's law of rotation. So with respect to that one, that means here what are we think we need to consider is, we need to consider the flux, we need to consider the torque, we need to consider the inertia, and we need to consider the angular position. So that's why we are taking. So T is the torque, and J is the inertia, theta is the angular position, and B is the flux. So according to that one, it is also based upon the inherently it is reflected to the Kirchhoff laws and everything also, but it is saying in terminologies of the mechanical itself. And the torque equals inertia time acceleration plus friction. So this is how it will be there. So totally that equation is related to this statement. And when it comes to the electromechanical relationship, that means what we are doing is we are combining, that means we are taking these two equations into consideration. So that whatever the back EMF is there, the back EMF is equal to the KB dt by dt, and also torque is there, that whatever is there, so KT of I into T. These are the two connecting currents with respect to the torque and other with respect to the speed of the voltage. So these relations we are taking into consideration. So we are linking these two things, and after that, how we are linking this, we are, if we are the d theta by dt and the dt I of t to I of t, like that we are considering. So then what we need to do is we need to convert this, all these mechanical equations into Laplace domain equations. So regarding that one, we are dividing the we are making the Laplace transform separately, electrical equation as separately, and also mechanical equation separately, to understand very clearly. So then taking Laplace transforms on that one, we input voltage VA of S equal to RA I of S plus LA S into I of S plus KB, that means the EBS into of theta S. And also in the same way, in the mechanical side, the input torque will be there, and with respect to the next inertia and also to the flux. So this is the mechanical and electrical Laplace transform based equations. Okay, when you apply the Laplace transform, then you can get these things. Then after that, after deriving the transfer function, what we need to do is we need to get the, from the mechanical equation, we need to get the current equation separately. So then only we can get the things. And also we need to separate this theta of S by K of VA of S. So then automatically we'll get the final transfer function equation. So to get the final transfer function equation, so as we already know, the input to the output. So input here it will is as a voltage, and output as the angular position of a motor. So that's why angular position of the motor is a theta of S, and input of the motor is a voltage, that is VA of S. So final transfer function is this one. So when this is the completely what we can say, it is a third order system. How we can define a third order system or second order system is based upon the denominator S, that S domain. Okay, here S cube is there, that means it is a third order system. If it is S square, that is a second order system. If it is only S will be there, that is a first order system. So based upon this one, the whatever the complexity of the motor can also be increases. Okay, that equation in a mathematical part. So the next one is about the transfer function, whatever it will be there. We need to sometimes we need to make a little bit of low equation, that means a simplification, we need to neglect the LA. That means what are the inductance is there, that is the that mostly the inductance of the motors will be very less. So that's why we are, what we are taking is we are neglecting that in inductor inductance. So then automatically what will happen, inductor based equation will be eliminated. So then the system will be considered into second order system, not in the third order system. Then automatically what will happen, to make analyzation, to make any of the understanding of the resistance changes, voltage changes, position changes, it easily can be identified. Then where we are actually, we are seeing this real world applications, so we are seeing this thing as many places, like it as a CNC mission, that means carbon natural gases missions, and also robotics, and also antenna based positioning systems, medical devices means I will show the example. So this is the thing, medical devices. So nowadays many people are not doing the operations, but this thing like it as if you are need to operating with respect to the monitor, it is operating the things. So this is can be done. This is a very real world application where you can able to see a DC servo motor operation. Okay, in the next lecture we are going to see the AC servo motor.